Before we talk about modern vehicle architectures, we need to reset our mental model. Traditionally, a car was not designed as one unified system. It was designed as a collection of independent electronic systems, each created to solve a very specific problem. One system controlled braking, another controlled steering, another handled lighting, comfort, or infotainment. Each system worked well on its own, but it had very limited awareness of what other systems were doing. This approach made sense when vehicle functionality was limited and change was slow. But as vehicles became more feature-rich, this same way of thinking quietly became a constraint. To understand why cars had to change, we first need to visualize this box-by-box way of building vehicles. If the car is a collection of independent boxes, the next question is obvious. Where does the control logic actually live? In traditional vehicles, control logic was distributed across the vehicle. Each major function was assigned its own electronic control unit, placed physically close to the sensors and actuators it controlled. Braking had its own control unit. Steering had its own control unit. Body functions, powertrain, and infotainment each had separate control units as well. This design choice was very intentional. Short wiring paths improved reliability, and each system could be developed and tested independently. But there was a hidden consequence. No single control unit understood the vehicle as a whole. The car only started behaving like one system very late in the project, when all these distributed units were finally connected together. And that delay between design and integration is where many real-world problems quietly begin. At this point, it is very important to pause and be fair to the traditional approach. The idea of one box handling one function was not a mistake. It was a very rational engineering decision for its time. Clear functional boundaries made systems easier to understand. Testing could focus on one problem at a time. Ownership was also very clear. One supplier delivered one electronic control unit responsible for one function. If something failed, accountability was obvious. There was also a safety advantage. By isolating functions in separate boxes, failures were naturally contained. A problem in one system was less likely to cascade into others. For vehicles with limited features and slow change cycles, this approach worked extremely well. The problem did not appear immediately. It only emerged when vehicles began to demand coordination, flexibility, and frequent change. The same isolation that made early development easier created a problem that only appeared much later. When systems are designed and optimized individually, they tend to work very well on their own. But vehicles do not operate as independent systems. They operate as one tightly coupled machine, especially when features begin to interact. In an isolated design model, those interactions are not fully understood early. They are discovered during integration, when all systems are finally connected together. And this timing matters. Late in the project, changes are slower, more expensive, and more visible. What looked like a clean architecture at the beginning often turns into long debugging sessions, unclear ownership, and uncomfortable trade-off decisions. This is the hidden cost of functional isolation. Not immediate failure, but delayed complexity revealed at the worst possible time. To understand why integration became difficult, we need to look at how systems talk to each other. In traditional vehicles, communication was signal-based. One system would publish a signal. Another system would read that signal. Each signal had a fixed meaning, agreed up front during design. This worked well when vehicle behavior was stable. Everyone knew what each signal meant, and nothing changed often. But signal-based communication has an important limitation. Every connection is predefined. If you want to change behavior, add a new feature, or reuse information somewhere else, you must update multiple systems together. Over time, vehicles stopped behaving like flexible systems and started behaving like hardwired logic diagrams. This is not a problem of speed or bandwidth. It is a problem of rigidity. And that rigidity becomes very visible as vehicles grow more complex. Once systems started exchanging signals, a new question appeared. How should all these systems actually be connected? The important point is this. Vehicles were never designed with a single network for everything. Different systems had very different needs. Some needed fast and deterministic communication. Others needed simple, low-cost messaging. Some needed high reliability, while others tolerated delay. Instead of forcing one solution everywhere, vehicle architectures evolved to use multiple networks, each chosen to match a specific set of constraints. This was a practical and sensible decision. It optimized cost, performance, and reliability for individual systems. But it also added another layer of complexity. Information now had to move not just between systems, but across different network boundaries. And as features began to span multiple systems, those boundaries became increasingly visible,